Right, can you see the slides on the screen? Okay, good, thanks. Right, so let's move on with reactive sputtering. So yesterday I did explain briefly about the difference between, hold on, let me approve your friends here. The difference between typical sputtering process, where you can sputter the sputter target material as it is in order to get your deposited layer. For example, if you want to deposit silicon nitride, for example, then the typical way of doing the sputtering is by having a silicon nitride target. Okay, silicon nitride target material, SiNX. Okay, SiNX target material, and then you sputter a silicon nitride from the target in order to get a silicon nitride thin film on your silicon, for example, or on a glass or on plastic or some other substrates. Okay, so that is the typical or the standard sputtering that we're talking about. And on the other hand, if you talk about reactive sputtering, you have to introduce a gas in order to induce reaction between the gas and the sputter target in order to produce a compound, for example. Okay, so in this case, if you talk about silicon nitride, to be able to produce silicon nitride through reactive sputtering, so that means you need to use silicon target material as your sputter target. Okay, and then at the same time you have to inject nitrogen gas into the chamber during the process. So then during the process, you're going to have a reaction between silicon and nitrogen, producing silicon nitride deposited on the substrate. Okay, so you can either deposit silicon nitride from the target or silicon plus nitrogen. That is called a reactive sputtering. Okay, reactive sputtering is introduced. Reactive gas is introduced in the sputtering chamber in addition to AR plasma. Okay, so you already have the plasma going on in the chamber, but then you introduce a gas that will eventually react with the sputter target in order to produce a compound. Okay, so compound is formed by elements of that gas combining with the sputter target material. So in this case, we're talking about silicon nitride as the compound. Okay, due to combination of the gas nitrogen and sputtered material silicon. Okay, so that means your silicon as your sputter target plus nitrogen as the gas introduced for reactive sputtering, producing silicon nitride. Okay, as a compound you intend to produce from this reaction. Okay, so there are cases where you need to use silicon nitride as your target material. There may be cases where you have to produce silicon plus nitrogen in order to get silicon nitride. So it really depends on what sort of properties are you looking at. For example, you may, if you are working on optical layer based on silicon nitride, then probably you are interested in the refractive index, for example, stoichiometry, extinction coefficient, ataupun kalau you guna untuk some thermal devices, maybe some thermal punya process parameters. Okay, so it goes down to what do you want to have at the end of the day, right? So silicon nitride nak guna untuk apa? Then what are the properties that are crucial in the deposited layer, okay, that you want to have? Okay, it's not only restricted to silicon nitride, can also be some other material ataupun some other compound. Okay, you try to search online now, and you try share in the chat box. What are the other examples of materials that can be reactively sputtered to form compounds? Okay, cuba search online. Sambil-sambil saya ajar ni, you can just search online example materials involving reactive sputtering. They can just write some equation, maybe silicon macam ni, silicon plus nitrogen, silicon nitride. Then what plus what equals what? Can write down in the chat box while I'm working on the next point. Right, plasma give energy to the gas to be dissociated. Okay, nitride, for example, if you talk about TiN, titanium nitride, nitride. In fact, we normally call it as nitride, TiN. Nitride formed by sputtering in sputtering titanium in the presence of nitrogen, for example. So in this case, kita pakai titanium sputter target material, and then in presence of nitrogen. So titanium plus nitrogen equals to tinitride, atau titanium nitride. Okay. Reaction occurs at the wafer surface and on the target itself. For example, titanium dioxide TiO2 reactive sputtering. Oxygen reacts with titanium on the target surface atom to form oxide there. Then it is sputtered onto the wafer. Okay, at the case where you can, where you are actually incorporating oxygen with the target material, and eventually they are sputtered off the target material to be deposited. Controlling the stoichiometry of reactively sputtered film is sometimes difficult. Apa maksud stoichiometry? If you're talking about silicon nitride, so that's the stoichiometry, X and Y. Okay, kadang-kadang you nak produce 1 to 3 ke, 3 to 4 ke, okay. The common one that we have is Si3 and 4. So this is the stoichiometry. So kalau you run reactive sputtering, silicon plus nitrogen, to ensure that you're going to get Si3 and 4 will be quite difficult, okay? Right, so titanium dioxide, thank you, Amirul. Titanium plus oxygen, TiO2. Other example, you will write down. So the key point here is to control the stoichiometry will be difficult with reactive sputtering. So that means you need to really optimize the process parameters involved, particularly the gas to be reacted with the target. Okay, maksudnya the flow rate of the gas in terms of SCCM, the time you introduce, for how long, all the stuff revolving around the gas will be very crucial in order for you to control the final stoichiometry of the deposited layer. Ada lagi ke? Other example other than TiO2 reactive sputtering? Have you found anything else? Okay. Al target plus oxygen jadi alumina, aluminium oxide. Okay, alumina. Al2O3, right? So that's another example. Ada lagi ke? If not oxide, ada lagi? Cuba tengok something else yang bukan oxide that can be produced by reactive sputtering. Right. Aluminium plus nitrogen, aluminium nitride, okay? Aluminium plus nitrogen, indium plus nitrogen boleh juga, indium nitride. All right, so let's see here some examples. Right, Juwaria. Nah, panjang list ni. Common compound reactively sputtered and the reactive gases employed are listed. Oxygen, banyak tu. Indium oxide, tin oxide, silicon dioxide, tantalum, Ta2O5, pentoxide, nitride, tantalum nitride, titanium nitride, silicon nitride, carbon nitride, carbide pada titanium carbide, tungsten carbide, silicon carbide, sulfide pada cat sulfide, copper sulfide, zinc sulfide, oxycarbide, oxynitride of titanium, tantalum, aluminium, aluminium, right? Maksudnya titanium oxycarbide, TiOC, right? Oxycarbide, maksudnya you ada oxygen, then you ada carbon, but then the oxygen and carbon tu ada dia punya stoichiometry. Just like Ta2O5 tadi, ya. But then you add on carbide, but with specific stoichiometry. Oxynitride, TiON, TiON, TiOX and Y, right? Stoichiometry. Al pun sama. Al oxycarbide, oxynitride. Silicon oxynitride. For example, SiON, Sion. Silicon oxynitride, SiON, OX and Y, right? So banyak lah. So we have many different materials that can be prepared by reactive sputtering. So that's the point. Right, another thing is, another important thing in this topic is called magnetron sputtering. Kita sputter, but then we run the sputtering by incorporating magnetron. Apa magnetron ni? Bukan megatron, magnetron. So in conventional DC and RF sputtering, efficiency of ionization from energetic collisions between electrons and gas atoms is low. Okay. So dalam typical system, the efficiency of ionization between electron and gas, but kita nak gas and electrons to react with each other to produce Ar plus, okay, Ar plus. But then the ionization efficiency is low, so that means the process of ionizing argon into argon plus always results in low efficiency. Maknanya tak semua you can ionize lah, right? So most electrons lose their energy in non-ionizing collision or are collected by the anode. Okay, electrons are lost. Few argon atoms are converted to positive ions. Okay, remember we want to convert argon to argon plus. Kita pakai argon gas, and you want to convert argon gas into argon ions or plasma. This Ar plus is plasma. So you need this plasma in order to initiate the sputtering process and sustain the sputtering process. Few Ar atoms are converted to positive ions and few positive ions strike the target. So few. So due to this low ionization efficiency, only few argon atoms are converted to positive ions. So only few are ionized, and then as a result, only few of Ar plus strike the target to initiate the sputtering process. Okay, so if you relate back to the previous discussion, I think 2 days ago, we talked about sputter yield again. Sputter yield, which depends on how many atoms are sputtered over every incident ion. Then you punya sputter yield will be reduced as well. So as a result, as a user, when you run sputtering process, you will see your sputter deposition rate will be low because of low yield. Okay, sputter rate, let's say you are expecting something like 50 angstrom per second, for example, then you probably end up with less than 10 angstrom per second. Okay, so that's like 5 or more orders of magnitude reduction due to the low ionization efficiency, for example. Okay, hold on, let me approve. Yeah, friend. Right. So in this technique, magnets are used to increase. With magnetron, what does it mean is magnets are used to increase the percentage of electrons that take part in ionization events. So remember, you want to use electron to collide with the argon plus and initiate the plasma, right? Start formation of plasma. So, but then the efficiency is very low. So problem statement ni ialah efficiency of ionization is very low. So macam mana kita nak increasekan ionization potential, ionization efficiency supaya you get to produce more Ar plus and you get to produce more plasma, and that will in turn produce higher sputter rate and sputter yield and so on. So to do this, one technique is called incorporation of magnetron to the sputtering. Okay, maknanya apa maksud magnetron? Kita tambah magnets. We add magnets, it's what we call magnetron, not megatron. If you're transformer punya betul fans. Magnets are used to increase the percentage of electrons that take part in an ionization event. So you have your, you can look at the picture on the right there. So you have your sputter target here. You have your sputter target. Oh, sorry. Ini your target. Then at the back, you incorporate magnetron. Supaya you can actually control the path of the electron in front of the target material in order to enhance collision. Maknanya you sort of pulling the electrons together to stay on the front side of the target material punya surface. Maknanya kumpulkan dia supaya you want to induce more collisions and initiate more plasma. Okay. So in this technique, magnets are used to increase a percentage of electrons that take part in ionization event, which is this. A magnetic field is applied at the right angles to the electric field by placing large rectangular magnets behind the target. Okay, so this is actually the magnetron. So kita ada magnet kat belakang ni. You're going to see later on in the next slide. So we are incorporating large rectangular magnets behind the target so that you are controlling ataupun you are pulling electrons in a path right in front of the target surface. Okay, when you kumpul dia semua dia langgar, you purposely accumulate them together in front. So in a magnetically confined plasma, electrons ejected from the cathode are confined. So you want to confine the electrons by the force, Lorentz force, to stay in the cathode dark space. Dekat depan ni lah, supaya you induce more collision on purpose. So that's called incorporation of magnetron. Okay. So what it does is it traps electrons near the target surface. So it traps electrons. So when you are seeing this, so that means it's trapping the electrons near the target surface, causing them to move in spiral motion, ikut dia punya path, until they collide with an argon atom. Okay, so you purposely kumpul dia supaya dia langgar dengan argon atom. So that's called magnetron. So ionization and sputtering efficiencies increase. So as a result, you get more ionization and you get more sputtering. So as a result, you get to see more yield, higher yield. As a user, you get to see higher deposition rate during the sputtering process. Ion density of around 0.03% compared to 0.001%. If you want to compare the increment, so that sort of increment is expected. Lower argon pressure can be utilized in order to improve better film quality. Usually kalau you pakai higher argon pressure in SCCM, then your films will be rougher. Dia akan jadi rough. If you, anyone did any AFM measurement last time during FYP? Ada buat atomic force microscope measurement, AFM? Anyone did AFM? Ada? Ada pakai ni AFM? So if you want to know the roughness of the deposit layer, for example, you can measure using AFM. Can measure using AFM. For example, if this is your silicon, this is your silicon wafer. So if you deposit a layer with lower pressure, low argon pressure, you normally get a more smooth film. Okay, when you deposit at higher pressure, you tend to get a bit rough films. Okay, so you can then tailor the properties of your deposit layer by playing with your argon pressure in this case. Planar and cylindrical magnetron system available. These are the configurations available. Target is eroded as material is sputtered away as shown on the right. Okay. So for example, if you see this, right? This is your target material. Target. Lakani magnet. This is the magnetron we're talking about. Behind the target. So ni plasma semua duduk kat depan ya. Plasma kat depan. Okay, plasma. So these are the paths of the electrons. Confined electron in the front side, on the front side of the target. A material inducing more collisions. So as a result, bila you punya electron to follow certain path in the front side, on the front side of the target, so you're going to get more reactions within the path. You akan dapat more reaction. Maknanya sputtering tu akan berlaku. Sputtering rate is enhanced, but then it will be very concentrated dekat magnetic punya field tu. Okay? Kat situ dia akan concentrated. Dekat tempat lain tu dia akan ada. Banyak juga if you compare to no magnetron at all. Tapi the concentration is not as much as within the field. Okay? Or in between the field, if you like. Okay? So as a result, due to that nature, you akan sputter more materials dekat area yang ada field. Okay? So you can sputter more because there are more reactions there, right? Very localized kind of reaction. So as a result, you can sputter that area more. Okay? Bila tengok sputter punya target dari atas, I don't have the sample. If you look at the sputter target material from the top, after some time, you will see dia ada macam bulatan, dia ada macam longkang lah, if you like. Kalau tengok di depan, let me see, di target material. If you ever see target material, then you akan nampak dia ada macam longkang sikit lah. Dia ada macam lubang sikit dekat certain radius, circumference dalam bentuk bulat, but then at certain radius dia akan ada. Because if you see that, dia nampak macam ada lubang sikit. That is the areas where your electrons are confined due to the presence of magnetron. Okay? Maknanya magnetic field tu dia akan concentrated kat situ, hence more collisions there, hence more sputtering there, hence holes kind of thing is created there, right? So the target is eroded. So ada longkang lah. We call that as target erosion due to the magnetron. You're not enhanced, but then if you're sputtering, uniformity, if you like, will not be exactly the same across the target material because it will be more concentrated where the electrons are confined. Okay. So ni pun sama juga. You can see this, pretty much the same thing. Ni dia punya a bigger illustration of the thing. Okay, for example, if you see, okay, dia ada magnet kat belakang. The magnet. So this whole chunk is the magnetron. Okay, so this piece is the target material. Say you want to deposit ITO, then that is ITO target. So these are the areas where electrons are confined. So that's why you get to see this erosion. And bottom you feel the concentrated guys too. So you get to see erosion of the target there. So kalau dari depan you akan nampak dia bulat lah. Dari cross section you get to see this whole kind of erosion, right? So that is due to the presence of concentrated electrons or confined electrons, right? Colliding with argon atoms, inducing a higher ionization efficiency during the sputtering process. Right, this is what I showed a few days ago. Lab scale, basically very small. You can see you can watch the video I shared yesterday dalam group WhatsApp. So lebih kurang dia sistem dia. Lab scale usually is very small. This is where you control all the parameters, the power, the recipe, the gas flow, well, everything. Okay, so this is the load log. This is the load log. Ni chamber yang nak sputter tadi. Ada electrode, ada plasma. This is glass window. So this is where you pump down to 10⁻⁵. So and then when you inject argon gas, it's got to be 10⁻⁵, or in the millitol region during the process. So this part, this is the gate valve. Ni sama macam sistem tadi semalam, more or less. This is the area where you get the load lock. Itu tutup gate valve ni. And the pressure on the left and pressure on the right will be isolated. Okay, then you can maintain the pressure in the chamber at 10⁻⁵ while you are venting the load lock, because sample masuk kat situ. So venting load lock means you are increasing the pressure from 10⁻⁵ up to atmospheric pressure so that you can open the lid. Kalau tak sampai dekat 180 atm, you can open the lid because it's still vacuum. Tak boleh nak cabut lah, right?
Bila dah sama dengan atmospheric pressure, there's no pressure difference between our ambient and the load lock. Then you can open the load lock, remove the sample, put new samples, tutup load lock, then push it down to 10 minus 5. Bila pressure load lock sama dengan pressure chamber, you can then open the gate valve because there's no pressure difference at all. Then you can just pull this arm ni, pull this arm, tolak je macam dalam video saya tunjukkan, tolak je, masuk sampel. Dia akan tolak sampel lah, robot arm. It's very manual because it's lab scale. Kalau dalam industry, it will be completely automated. It will just move itself, defined by the recipe loaded on the equipment, right? So tak ada lah orang tolak-tolak tu, buka gate valve manually. Kalau dalam lab scale kita memang buka gate valve. Kalau dalam macam UNSW dulu saya memang buka valve macam ni. Kat sini ni, you just pegang tu dah pusing. Save sampai dia completely open. Then you move the arm, transport, letak, align and everything. Sambut dia belah sini pun manual. Then sambut dia dapat sampel. Move the arm down so that it stays at the deposition punya position. Tarik balik arm tu manually. Tarik arm manually, keluar dengan tangan. Then you close balik gate valve tu. Reverse direction. Close gate valve. Then you isolate the chamber and the load lock. Then you start the process. Okay, start the process. Bila habis, buat benda yang sama balik lah. Buka balik, masuk arm, angkat sampel, ambil sampel, bawa keluar, tutup balik gate valve, maintain 10 minus 5 on the chamber, in the chamber, then you vent the load lock to 1 ATM so that you can remove the samples, right? Boleh tengok kat video tu, very simple illustration of how does it work. When you talk about industrial scale, it's very, very big, continuous, back to back. There's no manual handling at all. Okay, semua just automation. You letak je you punya disk or your wafer and then press the right recipe. Sometimes you don't even have to press. You just swipe card, click, swipe je your card, and it will detect what recipe to run, and then it will just continue, and it's done. Right, completely automated. Right, another area during the process or of the process that you want to learn is called biasing. Okay, what is biasing? Biasing means negative bias relative to the plasma is applied to the wafer. For example, maksudnya you apply bias to the wafer or the substrate lah, electrically isolated from chamber wall. Usually RF bias on the substrate is negative 50 to 300 volts. Okay, DCRF on target bias can be 700 to minus 2000. That's very high. Okay, so you can either bias the substrate ataupun you can also bias the target. Okay, jadi tengok sini ya, ni dalam chamber. So you can either bias, you can either bias the target, you can bias the target at whatever voltage. You can also bias the substrate that you want to deposit on. Silicon, glass, plastic, blah, blah, can also be biased. Tapi of course, you have to look at the substrate lah yang you can bias. So ada certain substrate are cannot be biased. It cannot be biased, right? So that's the range that you can bias. For example, substrate and target, right? So when I was in Fuji Electric last time, we used to apply bias to the to both, if I'm not mistaken. Okay, so dia ada dia punya rule lah. You can do that to either one or to both. Sputter etch and deposition on the wafer may occur concurrently. So, for example, if you are biasing the wafer to wafer kat sini ya, wafer is substrate lah. So if you're biasing the wafer, you use negative voltage, for example. So while the sputtering process is running, so that means you're running your sputtering macam biasa, but then at the same time you are calling ataupun you are attracting more argon. Sebab you bias negative kan, you bias wafer negative, so negative. So due to this biasing, you are attracting more argon atoms to the wafer, accelerated to the wafer. Maksudnya dia akan bombard the wafer lah. Okay, dia akan bombard the wafer. So wafer tu akan experience some sputtering. Okay, wafer akan experience some sputtering. And as a result of that sputtering, so you want a sputtering to take place to the target. You nak sputter target. Tapi bila you bias wafer, you are attracting AR plus to also hit the wafer. Okay, so then bila you activate biasing on the wafer, macam you are effectively sputter the target and at the same time sputter the wafer. Okay, and sputter the wafer we call that as sputter edge. Sebab kita nak deposit film on the wafer, and yet due to this biasing effect, you are also etching some materials from the wafer in order to tune the morphology or property or some other properties on the wafer. So that can be done. Okay, that can be done. So we call that as sputter etch. So we want to sputter to deposit layer, but then you are etching at the same time. So macam dua benda yang counterproductive lah. You deposit and yet you etch. Deposit and yet you etch. Why is it the case? So there are certain applications which require this sort of combination, right? So dia adalah dia punya, you might be depositing more than what you etch because of certain strategies that you want to do to get certain performance of your devices, perhaps, but that can be done. Okay, so all this while you've been learning about sputtering the target material so that you end up with films on the wafer. But sekarang you're sputtering the target material, but you are also sputter etch your wafer in order to produce certain properties of the materials. Okay, faham ke? This sputter etch punya concept, do you get it? Ataupun tak faham? Let's give some response. Faham tak sputter etch? Pening sikit, alright? Pening. Ada lagi tak pening? Ke yang lain okey? Yang lain okey ke? Ataupun semua pening? You pening, okay, right, that's right. So pening lah, okay, 3 orang pening. So saya kira semua pening lah, senang sikit. That's alright, that's fine. So this is your wafer. Macam dalam gambar kat bawah. This is your target. Okay, sebelum ni kita belajar, when you sputter, kita nak sputter target kan? Say this one is ITO. This is your silicon. You nak deposit ITO on silicon, right? So you want to use plasma to sputter ITO off the target material so that you can get ITO deposited on your silicon. Okay, nak kat bawah ni ITO deposit on silicon. So this is ITO, this is your silicon. But you can also induce biasing at the same time if you want to, if you need to. Tak semestinya. Kalau tak nak biasing pun, you can still get ITO on your silicon. Cumanya, in some conditions, you can also introduce negative biasing to the target material and also to the wafer. Okay, maknanya you can bias ITO, you can also bias silicon, right? So untuk case you bias silicon, conventionally we have been discussing about depositing ITO on your silicon, right? Deposit here. There's no biasing because you want to deposit. You want to add something. Deposit means you want to add something on the silicon. You bukan nak etch dia. Etching is removal, right? Tapi due to the biasing effect, bila you bias silicon, you are connecting silicon to negative 200 volt, for example, negative voltage. You are attracting more and more AR plus. We discussed last time about when you bias your whatever to negative, then you will attract more AR plus coming to the surface. So as a result, AR plus tu dia akan langgar you punya silicon ataupun perhaps ITO as well. Okay, depending on process step, how do you design the process recipe lah. So as a result, instead of just sputtering ataupun depositing layer of ITO on the silicon, you are actually etching the ITO at the same time. Ataupun kalau you buat lagi awal, you mungkin etch silicon dulu baru you sputter ITO, depending on the process recipe. Remember, each recipe typically contains, say, 7 to 10 steps of what's actually happening during the process. Maknanya dia akan follow exactly So you may also sputter etch your silicon ataupun you sputter etch your thin film of ITO on silicon in order to tailor ataupun to customize the properties of the ITO on the silicon. Maknanya, for example, kalau you deposit ITO macam biasa, there's no biasing, you may get certain level of sheet resistance of ITO on silicon because ITO is a transparent conductive oxide, degenerate semiconductors as we discussed last time. So it has to be transparent and conductive. So conductivity dia mungkin reflected by certain level of sheet resistance, right? Tapi bila you sputter etch ITO at the same time, mungkin dia punya sheet resistance reduces and that will result in higher conductivity because resistance is reciprocal to conductivity. So maknanya you boleh buat lah tu kalau that will improve the performance of the layer that you want to get. So that can be done, that can be explored, of course, right? So in fact, when we did this for a hard disk drive last time, we did some sputter etch punya concept by negatively biased the substrate yang kita nak deposit tu, right? So you are actually macam hentam dia at certain to certain extent, and that will tailor the properties of whatever they want to get. So in this case, berapa terabyte you can store, for example. Okay, so that can be done. Tapi conventionally, you don't have to do that. Tapi you boleh buat macam accessory je lah, right? Kalau that can improve the conductivity of your ITO, why not, right? So, but then you have to understand how does it improve? Due to roughness ke, due to whatever, it changed something, or does it change crystallinity of the ITO on the silicon by bombarding the ITO with air plus? Maybe, right? So that can be done. So that's the whole idea of biasing, right? So biasing can also planarize the film as pointed. Planarize the film and slope features that are being spotted, and slope features are being spotted more easily than horizontal vertical spaces. So it can also be used for planarization, right? So effect of substrate biasing, ni yang saya contoh tadi lah, right? So substrate bias, more energetic deposited atoms can also be done, right? Resistivity versus bias, ni boleh buat lah DC bias, RF bias. You can actually tailor the properties of the firms by biasing the process. So in bias sputtering, the ions incident on the surface of the wafer redistributed the deposit layer to improve step coverage. So it can also be used to improve step coverage, right? So you can also use your biasing to do annealing. Annealing, you heat up your sample in order to repair defects. For example, macam kita discuss on ion implantation, you anneal to restore the crystalline, the crystallinity of the silicon due to high energy bombardment of your dopant atoms yang akan menyebabkan you punya crystallinity jadi amorphous, right? Then you restore by annealing. So you can do annealing high temperature in a furnace to repair the defects. So bila you introduce biasing, the bombardment of AR plus to your sample can also result in high temperature punya nature. So bila you langgar, dia akan ada heat kan? Heat produced on the surface of the film, and that is considered as effectively annealing process as well. Okay, so dia akan introduce heat yang you akan dapat from typical conventional annealing process, but then this is from bombardment process, but that will equally produce heat as well. So that is effectively annealing, right? So from that you can actually you may produce larger grain size. So grain size, say if this is your SEM image of your CITO, okay. Kalau you tak ada bombardment, maybe you punya grain size is very small. Contoh je. Your grains without biasing, for example. But if you do biasing, same image, your sample, okay, your grain jadi besar, right? So as a result of annealing from the AR plus, so you bombard, the kind of heating effect. The heating effect is effectively macam you masuk sample dalam furnace lah at some temperature, which will increase the size of the grains, right? So it can also be used for this one as well. So maknanya annealing, biasing you pakai ni can be used for different purposes. For annealing, for crystallinity improvement, for step coverage improvement, for apa tadi? For collision, to tailor roughness, yeah, many more, right? So advantages and disadvantages of sputtering. Sputtering is more conformal than evaporation process. So we talk about conformality, we talk about directionality yesterday, right? Yang paling omnidirectional ialah CVD, yang paling highly directional ialah evaporation, right? Sputtering is always in the middle. So firm uniformity is more conformal than evaporation or sputtering, but it's less conformal if you compare to CVD, right? So another advantages, better thickness uniformity than evaporative deposition, evaporation lah, ED ni. Compatible with batch processing, easier stoichiometry control than evaporation, because you can also use multiple targets. You can sputter multiple targets. For example, if you want to deposit ALSI, for example, you can sputter AL, you can sputter SI, right? You can do together at one time. You can also do layer by layer. That means you deposit AL and then you stop, you shutter off, you block, turn on shutter. That means you block AL, then you deposit, you open shutter untuk silicon, you sputter silicon. You're going to get silicon on aluminium, for example. Can be used for almost any material, unlike CVD, because CVD depends on the gas. Okay, CVD is chemical vapor deposition. It's based on precursor gases coming into the chamber, right? Arriving atom have higher energies than evaporation, higher effective surface diffusivity, but can create subsurface defects. So bila you ada higher energy, the surface diffusivity will be higher as well, right? Disadvantages, subsurface defects can be generated due to the high energies. Same point, opposite point, same but then opposite lah. Sputtering and impurity gases are more likely to be incorporated. Okay, well, this depends, but possibility is there. Not good for epitaxial film, good for polycrystalline and amorphous film. Epi means you want to get monocrystal, monocrystal, single layer, thin layer, monocrystal. So it's not good by sputtering. You need to use some other system for epi, right? But it's okay if you want to use sputtering for polycrystalline, amorphous, silicon nitride, carbide, metals, right? So usually they go on sputtering. All right, finish. Okay, we finished sputtering. Any question on sputtering? We finished PVD. Hari Jumaat ni kita akan habiskan CVD. Okay, we have 2 hours, so we're going to do CVD, chemical vapor deposition. Then we're going to finish thin film deposition. Okay, let me just unshare. So when we finish chemical vapor deposition, okay, we only have like 2 big topics to cover. We have process after we finish CVD this Friday. So next week we're gonna go on process integration, right? So integration means how do you combine Nabi Bendola, right? Okay, that's all right. Okay, process integration is where we need to discuss how do you combine all the processes that you learned up to now in a typical process flow for IC fabrication. So how do you combine lithography, then etching, then implant, then diffusion, then oxide, all together as a process flow daripada mula sampai habis, right? Sekarang ni kita nak belajar almost all the processes. So you've covered oxidation, lithography, etching, diffusion, implant, thin film deposition, a bit on chemical mechanical polishing last time, planarization. Then yeah, we're going to learn on how do we combine all the processes or most of the processes for specific devices. Okay, so for this call, we're going to talk about IC fabrication, but in your presentation later on, you'll be assigned to present process flow for different semiconductor devices. So you will learn about solar cells, SSD, LEDs, maybe power devices, BJTs, okay, yang related to the industry that we have right now and perhaps the future industry as well. So tak ada soalan, eh? So I'll give you your assignment 2 today. The concept is like assignment 1. So you'll have like 2 weeks to finish online submission sama macam assignment 1. And then we're going to move on to your presentation punya assignment. Okay, minggu depan, I'll probably give you some time end of this week, but then you will have, I think 2 or 3 weeks. 2 weeks, I think 2 weeks, 2 weeks or 3 weeks to discuss among yourself. And then we're gonna schedule a time where each group will present your process flow for different devices. Kita akan adakan real time presentation, real time macam kita buat waktu 3 dulu. So each group will go. We're gonna have like two groups per session, hopefully. Satu kelas dua group, 20 minutes or so, and then Q&A. And then we're gonna finish in like 1 week. Presentation, Q&A, and then you'll be given your mark based on group presentation. Macam ZAT487 last time. Okay? Ada soalan? Ada? Alright, kalau tak ada soalan, then I'll see you on Friday, insyaAllah. Bye-bye. Take care. Assalamualaikum.